Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Question 51 states that imagine that your car is powered by a fusion engine in which the following reaction occurs, the one shown here, and gives the masses, which I will provide later. The engine uses 6.1 times 10 to the negative 6 kilograms of deuterium fuel. If 1 gallon of gasoline produces 2.1 times 10 to the 9 joules of energy, how many gallons of gasoline would have to be burned to equal the energy released by all the deuterium fuel? Okay, so first thing we'll do is look to see the energy produced in this reaction, and then we'll compare that to the amount of energy per volume of gasoline, and we'll take that ratio to find the volume required. Okay, so if we're looking for the energy released in this first reaction per quantity of, so the energy released per each of one of these reactions, so we'll call that E over N. That's simply the change in mass times C squared, again, per reaction. Just so I can save room, I'll just do it all in the same line. So looking at the mass of our final products, so value 4.0026 for helium-4, plus the mass of the proton, and the mass of the neutron. Subtract off 3 deuterium, 2.01141. Again, this is all absolute value. Oh, I should make that obvious. This looks like 14, which it's not. Absolute value times the, that's all with the units of U, multiplied by energy conversion factor, 931.5 MeV per U per C squared, multiplied by C squared. And we find that the energy released per reaction is 21.6 MeV, again, per reaction. But I recognize that our energy for the gas is in joules, so I should convert this to joules. And I know that's 1.6 times 10 to the negative 13 joules per MeV, which results in an energy released for each of these reactions in joules to be 3.46 times 10 to the negative 12 joules per reaction. So now, based on our mass, we can find out how many particles there are. So I guess we're told initially that we're given a mass for the amount of deuterium. However, in this response that we currently, or the value we currently calculated, this is for a single reaction, but there are 3 deuterium atoms in each reaction. So if we want this for a singular deuterium atom, we should divide this value by 3 for 3 deuterium atoms, we'll say. So our final answer really, for this scenario, would be 1.15. 1.15 times 10 to the negative 12 joules per, I'll give this in units, but really, again, this is for 1 deuterium atom, which is really what we're dealing with here. So now we can solve this reaction for how many atoms are present, or in this scenario, given by the relationship of mass over molar mass times Avogadro's number. If we use this, we can find the total energy for this reaction. So the total energy for this reaction is simply, obviously, our energy per reaction times the number of molecules, or atoms, I should say. And we can solve this fairly easily. our energy here. Again, 1.15 times 10 to the negative 12 joules per reaction, multiplied by the mass given to us. We'll put this in grams. So that's 6.1 times 10 to the negative 3 grams. Let me just actually, before I go on more, I'm going to divide this just so I don't get confused that this is a new line of thinking here. So again, substituting this value in for N. So this mass over the molar mass of deuterium, 2.0141 grams per mole, and Avogadro's number times 10 to the 23. I'll say N per mole. Reactions, whatever we're dealing with from previous. So N's cancel, 1/moles cancel, grams canceled, and we're left in total joules for this deuterium reaction, which is to two significant digits, 2.1 times 10 to the 9 joules. This looks awfully familiar. So now, based on, again, what we get from a gallon of gasoline, the total volume would simply be the energy produced in that first reaction divided by our energy per gallon, which if we look at our units, our values here, 2.1 times 10 to the 9, 2.1 times 10 to the 9. That was simply, if we divide those by each other, we would simply get a value of 1 gallon. And there you go. That's all it takes. 1 gallon of gasoline. Well, sorry, I should say, 1 gallon of gasoline compared to 6.1 times 10 to the negative 3 grams of deuterium, showing how much less is required of an atom compared to a volume of gasoline.